privacy. Matthew is giving the talk and is joint work with Jieming, Seth, and Roth.
All right, hi everybody. Let's just start. Okay, so the main motivating question for this talk is how much does interaction matter in local differential privacy? And the answer is going to be that it depends, and we'll give more specifics later, but that's like the overall answer. So we'll start with the basics of differential privacy, and then we'll move on to a narrower model, which will be local differential privacy, and then we'll actually talk about the results. So let's start with those basics. In words, differential privacy is a property of a randomized algorithm that says that small changes in the input to that algorithm only produce small changes in the output to that algorithm. And we achieve this guarantee by adding noise to the output to obscure small changes in the input. And in math, Seth just talked about this, so hopefully I don't have to spend too much time on it, but it's good to say it anyway. Two databases, X and X prime, are neighbors if they differ in at most one entry. And we'll say that the randomized algorithm A is epsilon delta differentially private if its output distribution on X versus its output distribution on X prime differs by at most this e to the epsilon multiplicative factor and this delta additive factor. So this is saying that the distributions are going to be close as parameterized by epsilon and delta. And this is private because if you think about X and X prime as respectively the database with and without your data, if A is differentially private, then the distributions of the output given X and X prime are close as parameterized by epsilon and delta, so the computation is effectively agnostic to your presence, and that's why it's private. And the cartoon that we're going to keep in mind for centrally private learning is there's like this stack of data, you have central access to it, you can just look at it, you do some learning, and then you add some noise and you produce some output. There are also two useful properties that Seth just talked about. One is composition. So if you have k, epsilon I, delta I differentially private algorithms and you run them on your data set, you can just sum up all the privacy parameters and get your overall privacy guarantee. The privacy guarantee overall might be better than that sum of parameters, but it's not going to be worse. The other thing about differential privacy is it's robust to post-processing, so if you take a differentially private output and then you sit and think about it for a while, you're not going to affect the privacy guarantee. And the benefit about these two guarantees is it makes differentially private algorithms like modular. You can cut and paste them together, and the overall algorithm you get at the end, its privacy guarantee will be like naturally inherited as a function of the privacy guarantees of its subroutines. So the key takeaways about differential privacy: differentially private algorithms map similar databases to similar output distributions, and they do this by adding randomness somewhere for privacy. And by the previous slide, they're like modular. You can cut and paste them together. So now we can move to the model that we actually care about in this talk, which is a more restrictive model called local differential privacy. So remember the centrally private cartoon where you have the central access to the data, you do some learning, you add some noise, you get some output. The cartoon for the locally private model is different in a few ways. So one thing you'll notice is like this stack of data is now slightly farther spaced apart. That's meant to represent that the data is now like distributed across devices. In particular, there's no like central repository that you can access. Instead, the data is distributed and you don't get to see it directly. And that's also what the arrows are meant to represent. You see the arrows of noise and learning have switched places in the local model. And that's because where in the local model, users are going to add noise to their data before they send it to you. So in the local model, there's no more central databases, no more central database. The users are going to keep their data. And the protocol, the differentially private protocol, is going to learn about the data through a public communication with the users. And the users are going to participate in this communication by using randomizers. So each communication they send will be sent through a differentially private function of a single data point. They're going to add randomness to their communication, and that randomness is what's going to make this whole thing private. So in math, we're going to say a protocol A is epsilon delta locally differentially private if the transcript of communications it generates, which is like a record of who said what at what time, is an epsilon delta private function of the data. So there are like pros and cons to this model. Some of the pros are that the data never leaves the user device. The user has full control over what they're sending, and they're only sending private output. So in particular, you as the user don't need to worry about like, oh, is my channel safe? You don't need to worry about like, is the third party running the algorithm safe? You don't have to worry about any of that. And the person running the algorithm no longer has to store private data. That also is good because you don't have to worry about being hacked or losing your user's data in the future. So those are like two nice things. But of course, these things come at like a cost. And one cost is that since people are adding noise at this individual level, there's just a lot more noise than in the central model. And this noise necessarily means worse utility than the central model. And you as the person like running the algorithm might be sad that you don't get to store private data because it means that in the future, if you want to do some other analysis on the data, you have to do a whole other communication. So there are pros and cons to this model. So let's remember the main point of this talk, which is how much does interaction actually matter in this model. So if we want to talk about interaction, we should probably like define the types of interaction there are. The simplest type is non-interaction. So in a non-interactive protocol, all the users are going to speak once, simultaneously and independently. So there's just one round of interaction. No one talks to anyone. There's just one round of output. The second type of interaction is a little more general. So now we still have each person speaking at most one time, but they can now do it in sequence. So in particular, like the fourth person who speaks can see the outputs of the first three people who spoke. And that's good because now there's a little more adaptivity in this process. And finally, the most general model is the fully interactive protocol. So here, there's just like no limits beyond local privacy. People can speak multiple times in multiple rounds. So those are the three types of interaction. In non-interaction, there's one round. In sequential interaction, the number of rounds is at most the number of users, because in each round, at least one person speaks, but also each person speaks at most once. In the fully interactive model, we just have no a priori bounds on the number of rounds. It could be like 1, it could be 50, it could be some huge number. We don't know. So most existing work on interaction and local privacy focuses on the relationship between non-interaction and sequential interaction. So like how much more powerful is sequential interaction than non-interaction? This talk is going to be about the relationship between sequential and full interaction. And this is like a dashed line because we show that in some cases, full interaction, not very powerful. In some cases, it is powerful. So our first result is about the limits of full interaction, what it can't get you. So informally, we prove that any fully interactive protocol can be converted into an identical sequentially interactive protocol with a controlled increase in sample complexity. So that's vague, but we'll say that the increase is sometimes small and it's sometimes large, and it's going to depend on something we call compositionality. So what is compositionality? Well, remember when we talked about the composition privacy guarantees. Composition is you cut and paste these randomizers together, and the privacy parameters for each randomizer are going to add up in that nice way we saw. So any algorithm that you analyze this way, any algorithm where you analyze it by just adding up the privacy parameters is going to be one compositional. But the important point is that that's not the only way to analyze an algorithm. So here's an example. Say that each user has a private piece of data, and that private piece of data is just like an element from some finite universe of size k. And you as the operator want to compute counts for the different elements. So you can come up with this protocol where each user is going to output a binary vector of length k, and they're going to do this in the following way. So for the index in the length k vector that corresponds to a true point, it's going to be a bit biased toward 1. And for every other index, it's going to be a bit biased toward 0. So it's like a random vector of length k that's like barely non-uniform. There's like one point where it's different. So visually, if the person's point was like the fourth thing, for every other index, they're outputting a bit from a distribution biased toward 0, but for the fourth index, it's a bit with a distribution biased toward 1. So you can analyze this in two ways. One way is just by composition, because for each bit, you can think about it as an epsilon randomizer. So when you think about it that way, okay, so there's k total epsilon randomizers. So you can just add up the privacy guarantees by composition. It's k epsilon, locally private. But you can also analyze it more directly. In particular, you can notice that there's only like, for any two outputs, they only have different distributions in at most two indices. So this dependence on, the dependence on k doesn't really make sense. Instead, you can just look at the output distributions, and most of it is going to cancel in the numerator and denominator, and you'll get this e to the epsilon ratio instead. So when you analyze it this direct way, you actually get an epsilon locally private guarantee. And we did this by taking advantage of this histogram data structure, where we know there's only like one spot in each vector that has this unusual quality. Okay, so now we have one algorithm and two ways of analyzing it. The composition way was k epsilon locally private, and the direct way was epsilon locally private. And this difference is what compositionality is about. So we say the compositionality of a locally private protocol is the multiplicative factor by which its minimal composition privacy guarantee exceeds the overall privacy guarantee. So here the composition privacy guarantee was k epsilon, and the overall guarantee was epsilon. So k epsilon over epsilon means the algorithm is k compositional. And this compositional quality is what's going to characterize our transformation. So the formal statement of our first result is that any fully interactive epsilon locally private k compositional protocol can be converted into an identical sequential protocol with an e to the epsilon times k blow up in the number of samples, and is the sample complexity of the original protocol. So we pay this cost that's parameterized by the compositionality of the original protocol. So one thing you can ask is like, okay, it's well and good to define this compositionality thing, but is it really like the right way to talk about these algorithms? Like, do you have to have this dependence on this quantity k? And so this brings us to our second result, which is about the power of full interaction. And what this result is going to say is that yes, this dependence on the compositionality k is necessary. And the way we prove this is by giving an example of a problem that we call multi-party pointer jumping. And so what this problem looks like is, imagine you have this very large tree of depth d, and for each node in the graph, it's going to be labeled with one of its children. So one of its children is the right node to take, but you don't know what it is. And each user knows the values for one of these levels. So you as the algorithm operator want to figure out the right node through the path, but you have to keep asking people to find out what that path, the right path through the graph. And you have to keep asking people to find that correct path. So that problem is multi-party pointer jumping. And what we show is that, okay, for one thing, there's a decompositional, fully interactive protocol that solves that problem using d-squared samples. The other thing we show is that any sequentially interactive protocol is going to require d-cubed samples. So what does that mean? Well, by the previous result, we can convert the decompositional protocol on d-squared samples into a sequential protocol that uses d-cubed samples. But that matches the lower bound for sequential protocols that we have here. So you can think about this and say, okay, so if I had a conversion with a better dependence on the compositionality, it would get a sequentially interactive protocol with fewer than d-cubed samples. So the fact that that's not possible means our dependence on the compositionality is necessary, up to log factors. So what these two results mean is that you can convert from full to sequential. There's this dependence on compositionality, but you can't avoid that dependence on compositionality. So here's like a slightly more concrete version of the question that motivated our talk, and it doesn't just depend, it depends specifically on this compositionality parameter. So what are the takeaways? One takeaway is that we can convert from full to sequential protocols, and the sample complexity blowup is going to be proportional to the compositionality of the fully interactive protocol. By the lower bound, full interaction can beat sequential interaction when the solution is highly compositional. Unavoidably highly compositional, but also highly specific problems exist. That's not really like a natural problem searching through a graph, but you can come up with it. One thing I should mention is we do have another paper that'll be in SOTA that improves this separation to an exponential separation rather than just polynomial. But for this paper, it's just polynomial. One thing I did mention in this talk, because it's like kind of orthogonal to the rest of it, is that we also get a separation between the local and central models for simple hypothesis testing, and the separation extends to approximate differential privacy as well. So if you're interested in any of those things, here is the paper, and that's all. Do you repeat that?
Like if I give you, like you have some algorithm and you want to like instantiate that result, like given an algorithm, like a DP algorithm, how hard is it to actually find out what the compositionality is?
So I'm not aware of any algorithms where the compositionality is like not well defined, but I don't know like how hard computationally it is to like determine that. It may be that it's hard to determine what the compositionality actually is. So in the sequential model, the like ith person to say something, they get to see all the previous outputs of the people before them, but in the non-interactive model, that's not true.
In sequential, like they get to learn all of those outputs before issuing their query?
Yeah, well, okay, so they know all the previous values before they say anything. Maybe we have different ideas of what query means. Do you mean like the protocol is telling a person what to say, or are you thinking about the like ith person in the protocol? Maybe I don't understand what query means. Yeah, so the thing that the query that's made at like the ith step can be a function of the previous responses, as long as it's in the sequential or full models. Yeah, so I agree that it would be good if, it's definitely better to have a protocol that doesn't have a bunch of rounds of communication. But I guess for this paper, we want to show that, we want to figure out if there are problems for which you definitely need a lot of rounds of communication. Ideally, we just show that for almost all problems, you don't need a lot of rounds of communication.
Also, like the non-interactive version is good because it's parallelized. and sequentially interactive. Is there like a refinement where like if I give you like 17 rounds, so
Yeah, so this is in the other Soda paper, but you can construct problems, basically a variant of pointer chasing, where it's like if you have 17 rounds, it's much easier than if you have 16 rounds. Yeah, for any number you want.
like that also depends on like positionality.
So that separation is between like sequential 17 and sequential 16. It's not a separation